Welcome back to the HVAC-Engineering-Techie channel. This is the channel that we talk all things HVAC, from engineering design, construction, equipment, systems, test and balance extensively, controls, efficiency, and system performance. Today's lesson is on HVAC duct pressure testing, exactly how you go about doing that, and why you do it and how you do it. So this should be helpful. These videos are educational in nature and are intended to help you in your career and help you on the job. So before we get into today's lesson, I'd like to thank you for being a subscriber. And if you're not, I'd really appreciate it if you'd subscribe by hitting the subscribe button down below and give me a thumbs up. That'd be appreciated. I'm not just searching for your data. I'm actually doing that because Google uses that data to evaluate this video. And that would really help me if you do it. It's totally free. No cost. It's totally painless for you, but it would really help me and I'd really appreciate it. Thanks. So let's get started on talking about HVAC duct pressure testing. So let's talk duct pressure testing. Duct leakage testing, which is called DALT, D-A-L-T, is actually done to make sure the duct isn't leaky, doesn't have a whole lot of leaks. So there's a certain standard out there we use. It's an ANSI SMACNA standard, and it's 016-2012. And this is the duct pressure testing standard. And the reason this testing standard was created in 2012 is before this date, everybody used different things like a certain percentage of the airflow or a certain percentage of the size of the duct or just different things that unfortunately completely different depending on what pressure you were testing and how much you were testing, duct you were testing. So eventually SMACNA said we have to have a standard, so they created the standard. This testing can be done by the installing contractor or it can be done by a tab contractor or any other third party that the contractor wishes to use. Duct pressure testing is done prior to the duct system being placed into operation and before insulation is placed on the duct. If you try to test it after the installation's on it, you can never find where it's leaking. You can tell it's leaking, but you can't tell where. So it has to be done that. It has to be done during installation because normally you have to chop the duct up into pieces. So you don't want a complete duct because you can't test a really large system. Our test rigs are only so large and they'll only do a certain length of duct. So you have to do this during construction. Each section of duct is selected to meet the test size limitations. How much duct can we do? And sealed where it is separated from the rest of the duct. And it's sealed at the normal openings for air outlets and duct takeoffs. So in other words, you take this piece of duct and you seal up the ends, put a test rig on it and test it. You can tell if that piece is leaking. Specifications will normally detail which ducts need to be pressure testing and to what percentage. We're going to test every piece of duct, or are we just going to select random samples and test those to see how leaky the general construction method is. And both are acceptable, except the specification needs to tell you what you need to do. So let's talk about the testing procedure. From the specification, determine which ducts are to be tested. And they might be the high pressure supply ducts, which is normally always, the medium pressure supply duct, which is normally always, low pressure supply duct, which is very, very seldom done because these ducts work at such low pressure that leaks don't affect much and they're always way down in the room, right at the end use. So if they leak a little bit, it's not a big disaster, but they can be tested depending on what it is. If the room's a laboratory, maybe you want to test them. Return ducts, almost never because they leak in, not out. Exhaust ducts need to be tested. They also leak in, but the problem is with the exhaust ducts, and the same with return, but not near as much, it impacts the size of the exhaust fan. If you have an exhaust fan to move 1,000 CFM and you have 300 CFM of leakage, now that exhaust fan has to remove 1,300 to be able to get the exhaust out of the room. So it's a big problem in exhaust duct. We don't normally test exhaust ducts, but we need to. We really should. What is the testing standard for test pressure and acceptable leak rates? What percent of duct needs to be tested? These need to be in the specification. What is the required testing schedule? When are these going to need to be scheduled? And this is why it's difficult for anyone other than the mechanical contractor to do the testing, because you don't really know when they need a test done. So if you're a third party, like a tab contractor doing this, you need to schedule with a contractor that makes sense. Like you're going to be there every Tuesday, or you're going to be there every other day, or you're going to be there, it depends when the mechanical contractor can have these sections ready for you. So this is why schedule is very important. What is the capacity of the pressure testing machine? This is critically important because it depends on how big your machine is, how much duct you can do, which dictates how big a piece you section off. So that all becomes really important. From the testing standard, determine the leakage class. Determining how large a section can be tested by calculating the surface area equal to about 90% of the pressure fan maximum capacity at test pressure. So you don't want to hook up a piece of duct that's just a little bit bigger than your fan because you'll never get to pressure. So you want to make sure your fan is bigger than the section you're going to test. So if you got a lot of leaks, you can still get to pressure and do the test. Can't get to pressure, you can't do the test. So that's important. On the drawings, break the duct system to be tested into sections that have less surface footage than the pressure the fan can handle. It's really important. Determine what pressure seals will be required for each test section. Because when you break a duct apart, you got to seal it, and that can become problematic, especially if you're testing at 4 or 5 inches. That's a lot of pressure, so your seals have to be tight and have to be structurally sound. Sealed sheet metal blank-off plates. So like if you're breaking a 48 by 24 inch duct apart, you're probably going to need a sheet metal flange heavy enough to seal off that end of the duct. It's not going to be a piece of cardboard. It's going to have to be something more substantial. Rubber seal blank-off plates for smaller, like 10-inch round or 12 by 12. You can use rubber. And there's certain types of rubber that have glue on it, so you'd use heat and you shrink it right on, and it sticks to the duct. The only problem with those are hard to get off, so you want to make sure some easy way that you can get it off. If it's real low pressure, you could use sticky tack material, but with duct tape around it to seal it. However, I would not do that because that's too susceptible to leakage and that'll fail your test. So here's the standard. Here's the pressure testing. So here's the duct class pressure. So what was that duct designed to take? And it might be 1/2 inch, 1 inch, 1.5 inch, or 2 inch water gauge. These are all in water gauge. And this is 1.5, 1.5, and 2 inch water gauge. This is 3 inch water gauge, and this is 4, 6, or 10 inch water gauge. If it's over this class, then if you have duct, you're going to test at 20 inches, like it's an industrial system or something. I would still use this class, and as long as it's not got contaminated material in it or something, it will probably be okay for transport. All right, so this is the seal class, and this is what's a general term for seal class, and then this is the actual number you're looking for. These are the numbers you want to know right down here. So this is duct that's unsealed. This whole column is unsealed. This column, traverse joints only, sealed. So that means the sections where the ducts put together in links, that's the traverse joint, and that has to be sealed to be this class. If you don't have any sealing, then it'll be over here this class. If you have seams and traverse joints, so your longitudinal seams are also sealed, then it's this class. If all joints are sealed and all penetrations are sealed, everything's sealed, then this is the best class you could get. So this is for rectangular duct. These are the classes for rectangular duct. This is round duct, and this is flex duct. Now flex duct can only go to this lower pressure. So these are the categories. And then this is the kind of a table I put together, maximum pressure. So what pressure do you test at? Well, if you have a duct that's a low pressure duct, 0 to 0.1 to 0.5 inches, then you can always test at the highest pressure, but never the lowest pressure. You always test at the highest pressure that's possible with that duct. But you don't want to go higher. You want to go just to that highest pressure because that's what it's constructed for. If you go higher, you may actually damage the duct. I remember one time I took a sheet metal guy and taught him how to do this, and I had a small blower. It's like a vacuum cleaner blower. This was years ago, and it was real small. It was like 1 horsepower, so it was real small. And I explained to him how to do that, and I got a call later today. He said, that fan blew up the duct. I said, what are you talking about? He said, well, it actually split the seam in the duct. I said, well, how long did you put it on? He said, well, we started it up, and I left to go do something else. I said, that's a 20-inch blower. That blower is capable of blowing 20 inches of pressure. So no wonder you blew the duct apart. He said, but it's too small. No, pressure doesn't matter by size. It matters about the type of fan it is. So when you do these tests, you need to stay right with it. You don't want to walk off. So always test at the highest pressure or it'll damage the duct. So if you have a 2-inch pressure system that's 2.1 to 3 inches, then you would test at 3 inches. If you have one that's 4.1 to 5 inches, you would test at 5 inches. If you have 6.1 to 10 inches, you test at 10 inches. So what you're doing is you're testing at the maximum pressure the duct is built for. Now the standard promotes something that no one does, which they should. The standard says that the design engineer is to put on the drawings what pressure class this duct is. They don't do that. So you have to kind of assume medium pressure duct is going to be 3 inches, 2 or 3 inches. You'll have to figure that out depending on what the fan is. If you have a fan that's producing 6 inches of pressure, external pressure to the unit, then it's got to be 6-inch duct. So you have to kind of back and check that out to see what pressure you're going to test. All right, so this is the testing procedure right here. Now this is a table. This is a cheater table here, which tells you if you have a test pressure down here and you have your leakage class up here. So let's say you have a leakage class, let's say 4. Leakage class 4, and you're going to test it. I have to figure out where I'm at here. 1 inch. So if you're class 4, 1 inch, then the factor is 4.0. That means you will leak 4 CFM per 100 square foot of duct with this class and that pressure. So that's a leakage class. That's how you determine how much you're leaking. Okay, first thing we need to do is once you know what test pressure you're going to be at, you know what leakage class you're going to be at because you know what sealing the contractor is doing, then you can figure out with what fan you have the maximum square footage of duct that you can actually test. So what you got to figure out is the perimeter area of the duct and then bullet times its length, and that will give you the it'll give you the area. So for the perimeter is the width times 2 and the height times 2, right? So that's the total perimeter of the duct. And then the P area, the perimeter area, is the perimeter divided, and we divide by 12 because the formula has to be in square feet, right? So we get rid of inches by dividing by 12 because these are just dimensions. And then times the length of the duct in feet. And that will give you the total area of the duct that you're trying to test. Now, normally for elbows and fittings, we go to the center line. We don't spend a lot of time agonizing over the exact square foot of an elbow, unless it's 20 foot by 10 foot duct, which I've only seen once. So it probably not that. Round duct, of course, is a perimeter equals pi times the diameter divided by 12. The diameter is in inches. And the area is that times the length of the duct. So that's round duct. And then flat oval duct's a little different. It's pi times the minimum dimension. This is the minimum dimensions. Plus 2 times Fs. And Fs is the flat surface area. And there's 2 of those, one here and one here. And that'll give you, divided by 12, gives you the square footage. And that times the length is what will give you a round flat oval duct surface area. That's what we're looking for, right? So these are the calculations you have to do on every job you're trying to test. All right, let's look at an example. So if you have a rectangular duct that's 24 inches wide and 14 inches deep and 98 feet long, what is the surface area? So it's W times 2 plus H times 2 divided by 12 times length. So it's going to be 24 by 2 plus 14 by 2 divided by 12 times 98, which equals 620 square feet. So we would have to have a fan that can do, and we'll get to that in a little bit, you have to multiply that times the leak rate, and then you can get where you need to be. So a round duct, of course, is perimeter. You have a 28-inch round duct that's 142 feet long. The surface area will be pi times d divided by 12, diameter times length, which equals 3.1416 times 28 divided by 12 times 142, which equals 1,040 square feet. A flat oval duct with a flat span of 48 inch and a minimum dimension of 18 inch and a length of 120 feet has what surface area? So using the formula, perimeter equals pi times minimum, which is in inches, times 2 times the flat span, which is in inches, divided by 12 times the length. So that would equal 3.1416 times 18 inches plus 2 times 48 inches, which is a flat area of the oval, divided by 12 times 120 equals 1,525 square feet. So how do we actually do the leakage rate? So if we have a 24-inch wide by 14-inch deep by 98-foot square duct, and this is the one we did before, and a class of 16 and an operating pressure of 1.5 inch, what is the maximum allowable leakage? And we take this chart and we find out the leakage class is 16, which means it's a traverse joint only sealed, and it's a square duct, so that's the 16. Okay, so we have this rectangular duct. We found out what the class is. Now we look at this table over here, and we have a class 16, which is here. We have 1.5 inches here, so the factor is 20.8. So the area is 24 times 2 plus 14 times 2 divided by 12 to get it in feet, times 98, which is 620 square feet. So per 100 feet, this is in per 100 feet. So we divide by 100 to get it to a factor times 20.8, and it comes to 129 CFM. So for this test, our fan has to be able to do 129 CFM at 1.5 inch static pressure. Now, we could have probably tested a lot larger duct than this, but this is the way it works out. So now for a round one, the 28-inch duct we did in the last one, 142 feet. And if you look at it, it's a class 8, and class 8 is here. And it's class 8, it's a test pressure of 2 inches, so 2 inches is 12.6. So here, the area is 3.1516, which is pi, times 28 divided by 12 times 142 is 1,040 square feet divided by 100 times 12.6 equals 131. On a flat oval duct, the same oval duct we did before, we have a 120-foot leakage, and we have a class 8 with an operating pressure 1.5. So for class 8, and we're 1.5, we're 10.4 factor. So here's that formula, which equals 1,525 square feet divided by 100 times 10.4, which is 159 CFM. Now, if you realize you did it at 1.5 inches, but if you were a class 48 instead of a class 8, you would be 8 times that. So you would be 900,000 CFM. So then you can see it really impacts you by what your class is. So let's say setting up the test. Once the test section has been isolated and sealed, set up the blower unit. So you got two kinds of blower. Well, you can have lots of blowers. These are a couple of commercially available units you can purchase, or you can build your own. But to build your own, you have to build the orifice. The Venturi orifice is the hard part. The rest of it's super simple. You can build that. But if you build your own orifice, then you have to calibrate the orifice. And you need to do that with some instrument that allow you to accurately test the CFM. I built, because I was doing large tubes, I built a 12-inch diameter one, which would do up to 3,000 CFM. I think it was 3,000 CFM to test really large. This is a large one. Well, this is a small unit. This is a larger unit, 9 to 1,400. This is 1 to 400. So you can do a bigger one. And I actually had one go to 3,000 CFM, so I can do great big duct. But so here's a section of duct we've broken off. And we put an end cap on the end with a flange on it for our pressure test unit, and a little probe to probe the pressure. And then we've temporary sealed here. We've temporary sealed there. We put a temporary seal here. Now you'll notice that I know always normal took a pressure test at the duct itself. These actually take it right at the end of the venturi right here, which is okay, except there could be a little bit difference between the pressure loss in this duct than if you do it right here. So that's why I always did it that way. So I got the real pressure in the duct. Never try to test with ACE units or terminal units in the duct section. So if this had a VAV box here, you could never test through a VAV box. Equipment, they leak a lot, so you don't want to try to test those. No terminal units, no air handlers, no fan coil units. None of that in the duct. You have to isolate it from those units because we're testing just the ductwork. So start the blower at low speed. Slowly increase the flow until the test pressure is achieved. You want to do it slowly because sometimes with a couple of things. One, You don't want to try to test too fast because you might actually might rupture some of your seals. But two, you may not get the pressure. So that's something you need to know. So you keep these. By the way, these test blowers all have VFDs on them, so you can do the speed change differently. So you can slowly up the speed, and once you get to pressure, stop, because you don't need to be over pressure. And then at that point, you read the flow meter. So you read what is the CFM you got blowing through this blower, because that's all leakage. So once you get to pressure, and if it leaks nothing, there's no flow, but it's still a pressure. But the flow coming out, if you're out of this Venturi, that's what your leakage actually is. So now you want to document what section of duct this is, the test pressure and the leakage flow. And here's kind of a test record, and you can make this look any way you want. It's just these were the sections we're testing. This is the operating pressure. This is the leakage class. This is the leakage factor per 100 square feet. This is the duct section square feet, the absolute leakage rate, the test pressure, and the actual leakage. And you'll see two of these didn't work. They're too leaky. So those that's why I have them in red. They didn't actually pass. So at that point, if it fails, if a test does not get the test pressure, that's the first thing. If it doesn't get the test pressure, first thing you always want to do is check your air supply hose for kinks or obstructions and to make sure it's not leaking. What happens a lot of times is these units are used on lots of different jobs, and they might get a little rough with them and put holes in the flex duct. And that's a leak, and you don't want that leak. So you certainly don't want your flex duct leaking. You want to check the meter connections and make sure there's not something wrong with the meter connection. Or you want to check the tubes to make sure the tubes don't leak, and then verify the duct section is not too large for the blower. That's what normally is wrong. We made a mistake somewhere along the line. We have too much area, and that blower won't ever get there. Too high of leakage flow. I mean, if it's too high of leakage, and you want to select the hose connections again, because if those are leaking and it's got way more air going to it, it's not the duct section, it's your hose. Check the duct section for audible leaks or open holes. And normally you can do that. You can normally, if you get close enough, you can hear the duct leaking as long as you're not right next to the blower. And check temporary seals for leaks, because a lot of times your leakage is at your seals. And obviously we don't want that failing a test, so you have to reseal it. So if you find a leak, then we need to seal it and then redo the test. Re-verify the duct surface area and factors. Make sure we haven't made a mistake arithmetically and that we're okay on this. If the duct area is too large, then the blower will not be able to achieve the pressure. If the test factors are incorrect, flow may be higher due to too much duct area. So we want to check to see we did everything right. And then the final view is, of course, if it's got too many leaks, we got to reseal the duct. So I hope that was helpful. Again, if you want those tables, just stop the video and clip those out of there, or do a screen save. That's an easy way to get the tables. So thank you for watching. Appreciate you being a subscriber. Thank you very much. I'll catch you on the next one. Thank you.